service calculations in the National Electrical Code, or NEC, are primarily intended to assist electrical designers and installers in properly sizing service equipment such as service panels, meters, and conductors. These calculations are based on the anticipated electrical load of the building or facility, which is derived from load calculations. While it is true that utility companies may have their own rules for sizing service entrance equipment, this does not render the NEC service calculations useless. The NEC calculations provide a standardized method for determining the minimum required capacity of service equipment, regardless of the utility company's specific requirements. Utilities often use demand factors and other parameters to determine the actual size of service equipment they provide. However, these factors are often conservative and may result in oversized equipment. By performing NEC service calculations, designers can ensure that the service equipment installed in the building site is adequately sized to handle the actual electrical load, even if the utility company's equipment is larger. There are several benefits to performing NEC service calculations, even if the utility company specifies the service entrance equipment size. Firstly, NEC service calculations help ensure compliance with electrical codes and standards. Secondly, the calculations determine the minimum required capacity of service equipment, allowing designers to select appropriately sized equipment that is neither undersized nor oversized. Thirdly, properly sized service equipment can reduce energy losses and improve overall system efficiency. Fourthly, adequate service equipment prevents overloading and ensures proper electrical protection for the building or facility. Authorities having jurisdiction, or ODs, are responsible for enforcing electrical codes and standards. As such, AHJ typically require service calculations as part of the plan approval process. This is to ensure that the service equipment installed is compliant with the NEC and can safely handle the electrical load of the building. While utility companies may have their own rules for sizing service entrance equipment, the NEC service calculations remain an essential part of the electrical design process. These calculations provide a standardized and reliable method for determining the minimum required capacity of service equipment, ensuring compliance with codes, safety, and energy efficiency. AHJ play a vital role in enforcing these requirements by requiring service calculations as part of the plan approval process. Let's delve deeper into the specifics of NEC service calculations and how they relate to utility company practices. The NEC provides a framework for calculating the total load of a building, considering various factors such as lighting, receptacles, appliances, heating, ventilation, and air conditioning, or HVAC, systems, and motor loads. These calculations are based on the NEC tables and guidelines, which specify the demand factors to be applied to different types of loads. Demand factors are essentially multipliers that reduce the calculated load to account for the fact that not all electrical equipment will be operating at its maximum capacity simultaneously. For example, a large office building might have hundreds of receptacles, but it is unlikely that every single receptacle will be in use at the same time. Therefore, the NEC allows for a demand factor to be applied to the receptacle load, reducing the overall service load calculation. Utility companies, on the other hand, often use their own demand factors, which may differ from those specified in the NEC. These demand factors are typically based on the utility's historical data and experience with similar types of buildings or facilities. In some cases, the utility's demand factors may be lower than those in the NEC, resulting in a smaller service entrance equipment size. This is because utility companies are primarily concerned with the peak demand that they need to supply, rather than the total connected load of the building. The peak demand is the maximum amount of power that the building is likely to draw at any given time. While the NEC focuses on ensuring that the service equipment is adequately sized to handle the total connected load, the utility company focuses on ensuring that its system can handle the peak demand. This difference in perspective can sometimes lead to discrepancies between the NEC service calculations and the utility company's requirements. However, it is important to understand that both the NEC and the utility company are working towards the same goal, which is to provide a safe and reliable electrical supply. The NEC service calculations are designed to protect the building and its occupants from electrical hazards, while the utility company's requirements are designed to protect the utilities grid from overloads. In most cases, the NEC service calculations will result in a larger service entrance equipment size than what the utility company would require. This is because the NEC errs on the side of caution, ensuring that the service equipment has sufficient capacity to handle any potential load. The utility company, on the other hand, may be willing to take a slightly higher risk of overload, as long as it is confident that its system can handle the peak demand. It is also important to note that the NEC is a minimum standard, meaning that it sets the minimum requirements for electrical safety. Designers and installers are free to exceed these requirements if they believe it is necessary to do so. For example, a designer might choose to install a larger service panel than what is required by the NEC in order to provide additional capacity for future expansion. In some cases, the utility company may require the designer to install a larger service entrance equipment size than what is required by the NEC. This could be due to the utility company's specific requirements, or it could be due to the characteristics of the utilities grid in that area. In these cases, the designer must comply with the utility company's requirements, as the utility company has the ultimate authority over the service entrance equipment. However, the designer should also ensure that the service equipment complies with the NEC, as the NEC is the governing standard for electrical safety. The AHJ plays a crucial role in ensuring that both the NEC and the utility company's requirements are met. The AHJ is responsible for reviewing the electrical plans and inspecting the electrical installation to ensure that it complies with all applicable codes and standards. The AHJ will typically require the designer to submit service calculations as part of the plan review process. These calculations must be based on the NEC guidelines and must demonstrate that the service equipment is adequately sized to handle the anticipated electrical load. The AHJ may also require the designer to provide documentation from the utility company indicating the utility company's requirements for the service entrance equipment. If there are any discrepancies between the NEC service calculations and the utility company's requirements, the AHJ will work with the designer and the utility company to resolve them. In some cases, the AHJ may require the designer to revise the electrical plans to comply with both the NEC and the utility company's requirements. In other cases, the AHJ may grant a variance from the NEC, allowing the designer to deviate from the NEC requirements. However, variances are typically only granted in exceptional circumstances and must be justified by sound engineering principles. It is important for electrical designers and installers to understand the roles of the NEC, utility company, and the AHJ in the service entrance equipment design process. By understanding these roles, designers and installers can ensure that the service equipment is properly sized, safe, and compliant with all applicable codes and standards. Let's consider some specific examples of how the NEC service calculations and utility company requirements can interact. Imagine a small retail store with a total connected load of 100 amps at 240 volts. According to the NEC, the service entrance conductors must be sized to carry at least 100 amps continuously. However, the utility company may have a demand factor of 0.8 for retail stores, meaning that the utility company only expects the store to draw 80 amps at its peak. In this case, the utility company may allow the store to install a smaller service entrance equipment size than what is required by the NEC. However, the designer should still ensure that the service entrance conductors are sized to carry at least 100 amps, as required by the NEC. This will ensure that the service equipment has sufficient capacity to handle any potential load, even if the utility company's demand factor is lower. Alternatively, consider a large manufacturing plant with a total connected load of 1000 amps at 480 volts. According to the NEC, the service entrance conductors must be sized to carry at least 1000 amps continuously. The utility company may have a demand factor of 0.9 for manufacturing plants, meaning that the utility company expects the plant to draw 900 amps at its peak. In this case, the utility company may require the plant to install a larger service entrance equipment size than what is required by the NEC. This could be due to the utility company's specific requirements, or it could be due to the characteristics of the utilities grid in that area. The designer must comply with the utility company's requirements, as the utility company has the ultimate authority over the service entrance equipment. However, the designer should also ensure that the service equipment complies with the NEC, as the NEC is the governing standard for electrical safety. In addition to demand factors, utility companies may also have other requirements that affect the service entrance equipment size. For example, utility companies may require the installation of transformers, surge protection devices, or power factor correction equipment. These requirements can all affect the size and configuration of the service entrance equipment. It is important for designers and installers to consult with the utility company early in the design process to determine all of the utility company's requirements. This will help to ensure that the service entrance equipment is properly designed and installed. In summary, the NEC service calculations are an essential part of the electrical design process. These calculations provide a standardized and reliable method for determining the minimum required capacity of service equipment, ensuring compliance with codes, safety, and energy efficiency. Utility companies may have their own rules for sizing service entrance equipment, but the NEC service calculations remain important for ensuring that the service equipment is adequately sized to handle the actual electrical load. AHA play a vital role in enforcing these requirements by requiring service calculations as part of the plan approval process. Understanding the interplay between the NEC, utility company requirements, and AHA regulations is crucial for successful electrical design and installation. Consider the specific NEC articles that relate to service calculations. Article 220 covers branch circuit, feeder, and service calculations. This article provides the guidelines and methods for calculating the loads that will be served by the electrical system. It outlines both general requirements and specific requirements for different types of occupancies and loads. Article 230 addresses services. This article covers the requirements for service conductors, service equipment, and overcurrent protection. It specifies the types of wiring methods that are permitted for service conductors, the location of service equipment, and the requirements for grounding and bonding. Within Article 220, several sections are particularly relevant to service calculations. Section 220.12 covers general lighting loads. This section specifies the minimum lighting load requirements for different types of occupancies based on the square footage of the building. Section 220.14 covers other loads, including receptacle loads, appliance loads, and motor loads. This section provides the methods for calculating the loads of these various types of equipment. Section 220.42 covers general lighting demand factors. This section allows for demand factors to be applied to the general lighting load in certain types of occupancies, such as office buildings and retail stores. Section 220.80 covers optional method calculations for dwelling units. This section provides an alternative method for calculating the service load of dwelling units, which may result in a lower calculated load than the standard method. Within Article 230, several sections are also relevant to service calculations. Section 230.42 covers size and rating of service entrance conductors. This section specifies the minimum size of service entrance conductors based on the calculated service load. Section 230.70 covers general requirements for service equipment. This section specifies the location and accessibility requirements for service equipment. Section 230.90 covers overcurrent protection requirements. This section specifies the requirements for overcurrent protection of service conductors and service equipment. When performing service calculations, it is important to carefully review all of these relevant NEC articles and sections. It is also important to consult with the local AHA to determine any local amendments or interpretations of the NEC. Remember that the NEC is a living document that is updated every 3 years. It is important to stay up to date with the latest edition of the NEC and any applicable local amendments. Proper service calculations are essential for ensuring the safety and reliability of electrical systems. By following the NEC guidelines and consulting with the utility company and the AHJ, designers and installers can ensure that service equipment is properly sized and installed.